A very interesting thing about light is that it has this dual nature. It has this particle-wave duality. We already looked at its wave nature, where we can find its frequency or its wavelength, and using the speed of light, right? The constant for speed of light. Now, there's something that we can't determine with that particular equation, and that is how much energy is possessed by this light, how much energy is being carried. Now, there are a few additional details that we need to cover. There's something that we call a light particle, which is very strange, but it's called a photon. A photon is a light particle. It's really kind of an electron that has enough energy to emit light. And that amount of energy that a photon has is a quantum. So a quantum of energy is a very, very, very small amount of energy. It is really the amount of energy required for an electron, look back at our model here, for an electron that an electron must absorb for it to go from one energy level to the next. It's this small measure of energy. What if we want to determine how much energy is really there for a particular wavelength or frequency of light or radiation? The equation for this is going to be the energy of a photon, which is the same thing as the energy of a quantum, equals h times nu. Now, we know nu is frequency. Okay, remember that from the previous video. This is frequency, and this is going to have units of hertz or waves per second or 1/second, which is the same thing as seconds to the -1. Okay. H is something called Planck's constant. Now, I'm not particularly interested in you remembering the history of Planck's constant, and you don't actually need to know the exact value. I will provide that to you. 6.626 times 10 to the -34 joules per second. Now, joules is the unit that we will use for energy. So this is our unit of energy. So our final answer when we're looking for the energy of a photon or energy of a quantum should be in joules. Now let's see if that really works. If we have Planck's constant, in which case we have units of joules times second, so that's joules times second, and we're multiplying that by frequency. And I'm going to use this 1/second. Multiplying by 1/second, now we have seconds in the numerator, seconds in the denominator, in which case they cancel out. And joules times 1 is just joules. So when you multiply Planck's constant times frequency, you will get a unit of joules, and that is how much energy is carried by a photon that is at that frequency. So let's look at an example of this and do the calculations. So in the previous video, we did an example where we found the wavelength of radiation with a frequency of 3.2 times 10 to the -2, and this was hertz. And remember, or it could be 1/seconds. Okay, so that's frequency. And let me rewrite our equation for energy. So energy of the photon equals h times frequency. So if we are trying to find the energy of the photon, we are multiplying Planck's constant times frequency. Planck's constant being 6.626 times 10 to the negative 34 joules times seconds. Multiply that by 3.2 times 10 to the negative 2, and I'm going to write 1 over seconds. So now our seconds cancel out, which we already talked about, and our final unit is joules. And when we looked at multiplying with scientific notation, we said that these coefficients are going to be multiplied and these exponents are going to be added. So let's get out our calculator, and we'll do 6.626 times 3.2, in which case we get 21.2032. 21.2032 times 10 to the negative 34 plus negative 2. So plus negative would be the same thing as minus, so it would be 10 to the negative 36 joules. I want you to realize this is an extremely small number. I mean, very, very, very tiny. It's also not in correct scientific notation. You would want to move this over, so you have 2.12032 times 10 to the what? This number got smaller, so this number needs to get bigger, so it'll be negative 35 joules. And again, it doesn't have the correct number of sig figs. We have 3.2. That's only 2 sig figs. We're going to round it to 2.1 times 10 to the negative 35 joules. A very, very small amount of energy that is being carried by this photon that is at 3.2 times 10 to the negative 2 hertz of a frequency. Now, be sure you can kind of get an idea of how these two equations can come into play with one another. If we have, I'll erase that too, if we have C equals lambda nu, and we have E equals h nu, then I should be able to give you the wavelength of a type of radiation, and you need to find the frequency, and from that you need to find the energy. So I can ask you how much energy is carried, or does a photon is carried by a photon with a wavelength of, let's say, 3.7 times 10 to the negative 3 meters. So that's our question. How much energy is carried by a photon with a wavelength of 3.7 times 10 to the negative 3 meters? Here's our wavelength. Here's our energy. The only thing these two equations have in common is frequency. So the thing to do here would be to solve for frequency and then solve for your energy. So let's do that. We have lambda, our wavelength. Oh wait, no, I've given you wavelength. So we're solving for frequency. That's nu equals C over lambda equals 3.00 times 10 to the 8th meters per second divided by wavelength, which was 3.7 times 10 to the negative 3 meters. Now I want you to notice again our units. Meters cancel out, so we have per second left. And that's the same thing, so 1 over second is the same thing as hertz, and that is an acceptable unit for frequency. So let's do 3 divided by 3.7, and I'm going to do it on my calculator over here. I got 0.810810, and it just continues. This is a repeating number. Times 10, and remember with division, you do 8 minus negative 3. So minus negative means plus. So 8 plus 3 is 11. So 8.10810 times 10 to the 11th, and I'm going to say hertz. Okay? Just because it's easier, but you can keep writing per second. Now, look at this. It is not in the correct scientific notation, so I'm going to move the decimal to 8.10810 times 10. This number got bigger, so this number will get smaller, times 10 to the 10th hertz. And here we only have 2 sig figs, so we need to round this to 2 sig figs, meaning we will just cut this right out. And now we have 8.1 times 10 to the 10 hertz. From here, we can figure out our energy. So energy equals Planck's constant times frequency. And we know Planck's constant to be 6.626 times 10 to the negative 34 joules times second. Multiply that by 8.1 times 10 to the 10th. And I know I wrote hertz here, but again, when I see times seconds here, I want to put in a unit that will match up with that. So I'm going to say per second. And now those seconds cancel out, and our final unit is joules. Remember, with division, we're going to, with multiplication, we will multiply this coefficient with this coefficient. So 6.626 times 8.1 equals 53.6706 times 10, and we do negative 34 plus 10. So that's going to be to the negative 24th joules. Again, make sure that it's in scientific notation, so move over your decimal place. It's 5.36706 times 10. This number got smaller, so this number needs to get bigger. Negative 24 will get bigger. It's negative 23 joules. And again, looking at sig figs, do not forget about your sig figs. Here we only have 2 sig figs, so we're going to round this to 2. Notice that after this 3, we have a 6, so we're going to have to round up to 5.4 times 10 to the negative 23 joules. So now you know that a photon that has a wavelength of 3.7 times 10 to the negative 3 meters is carrying energy, has energy of 5.4 times 10 to the negative 23 joules. Okay, make sure that you can do problems like this one. Feel free to try out some of the practice problems that I've listed for you to try, and come to class ready to ask any questions.